as I mentioned, we were talking about the general logarithmic function and the general exponential function. And last time we were down to this one last example. So admittedly, this is a tricky example, and I wouldn't put something like this on a final exam, but I did want you to see how this example goes. Also, I did want to show you a variation of logarithmic differentiation in this example. So in this example, we're asked to evaluate this definite integral, the definite integral from 1 to 2 of x raised to the 2x times quantity 1 plus natural log of x dx. So it looks like quite a mess, but actually it turns out to be pretty nice. So if we first write x to the 2x as x raised to the x plus x, and then we can split that up and write x to the 2x as x to the x times x to the x. So why am I doing this? Because I already know how this problem goes. This isn't necessarily an obvious move. It's just what works. And I just want to show you what works here. So we rewrite this x to the 2x as x to the x times x to the x. And the whole reason we did that is because we now want to use a u substitution. I now want to let u equal x to the x. Like I said, this is a tricky problem. It's not necessarily obvious to do this. And so now we need to find du. So I need to find a derivative. And so, I hope you're noticing that because this is a variable raised to a variable, I can't just do a power rule on it. Technically speaking, to do the derivative here, we need logarithmic differentiation. So I need to take the ln of both sides and then bring the x down and then do an implicit differentiation. So here I want to show you a slightly different technique. It's still logarithmic differentiation, but just a slightly different form. So here, I want to use the fact that we can always write, for any positive number, we can always write a equals e to the ln of a. Because e and ln are inverses, they would cancel, it just gives you back a. So I want to use this trick here. So here, the x to the x, I'm going to write this as e to the ln of x to the x. And then using properties of the log, I'm going to bring this exponent down in front. So then I have x to the x equals e raised to the x ln of x. So this is the variation I'm talking about, where I'm rewriting it as e to the ln of x raised to the x, and then using properties of the log to bring down the x that was in the exponent. And now we can just take the derivative directly. Here, I can think of this basically as an example of a function of the form e to the u of x. And we know for this, the chain rule, I'm just going to do the derivative of the outside will be e to the u of x, and the derivative of the outside will be e to the u, times the derivative of the inside will be u prime. So that's exactly what I'm going to do here. So here, derivative of the outside, remember derivative of e to whatever is just e to whatever. So I just copy down the e to the x ln of x. That's the derivative of the outside. And now we want to do the derivative of the inside function, which is this x times ln of x that's right up here. And when you're taking the derivative of x times ln of x, I hope you say, aha, that's a product rule. And so that's what's happening here, a product rule. Derivative of the first times the second, plus I copy down the first function times the derivative of the second function. The second function is ln of x, and the derivative of ln of x is 1 over x. And so now, I just put this together. 1 times ln of x is just ln of x. X times 1 over x is 1, and I put that in the front. And here, the e raised to the x ln of x, I wrote it back in its original form, x to the x. And here, how does that work? So let's just practice this. Take the x that's in the front and put it up here using properties of log in the exponential position. Then you have e raised to the ln of x to the x, and the e and the ln cancel, and we just get x to the x. And so now we see, this u substitution will work because this x to the x times 1 plus ln of x dx is exactly a term that appears in our integrand here. And so this part will completely be converted into du, and there's still another x to the x that will be converted into u. And so here, this shows we will be able to convert the integrand completely into the u variable. We just have to also convert the bound. So let's not forget here, we have, the bounds going from 1 to 2. These are in the x variable, we want them in the u variable. So using the substitution, u equal x to the x, I can plug in x equal to 1 and get the bound in terms of u. So when x is 1, I have u is 1 to the 1, or u is just 1. And similarly, when x is 2, I plug in, I get u is 2 to the 2, or 4. And so now we can completely convert the integral. This messy looking integral, 1 to 2, x raised to the 2x times 1 plus ln of x dx. First, I factor the x to the 2x as x to the x times x to the x. And we can now do the complete u substitution. I convert it. Don't forget to convert the bounds. So I have definite integral 1 to 4 of, so this first x to the x becomes a u. And then the remaining terms, x to the x times 1 plus ln of x dx, that becomes our du. And so this very messy integral becomes a very simple integral. We know u squared over 2 is an antiderivative. And then I can do f of b minus f of a. And that finishes the problem. So undoubtedly, this is a tricky question, but I think this little trick right here, where we write x to the x as ln, e to the ln of x to the x, and then use properties of the log to simplify that, and then take a derivative. I think that's an important technique to also know. It's essentially logarithmic differentiation, because logarithmic differentiation is we take the logarithm and then use properties of the log to simplify and then differentiate. That's what we've done here, except we didn't take the log of both sides. We did an e to the ln on one side. So I'll let you think about that. And so that ends our discussion of the general exponential function. And so now we want to specifically talk about exponential growth and decay. And so when I say we want to talk about exponential growth and decay, this is an example of what we call mathematical modeling. So this is really the first time we've really talked about, seriously at least, how do we use the math that we've learned to describe the world around us? And so that's called mathematical modeling. And it typically has 3 steps. And I refer to it as an art because it's not that easy or that obvious. It really takes a deep understanding of both the physical phenomenon that you're trying to model, as well as the math, and being able to put those two together. So here, the first step involves translating a real world problem into math. And typically it's an idealized real world problem. So we ignore certain things like friction or something like that, just to make it a simple, manageable model that I can convert into mathematics. Then we solve that math problem. Okay, so we've taken this real world problem, we've converted it into a math equation, then we solve the math equation. Once we've solved the math equation, then we want to interpret the mathematical solution in terms of reality. So, in step 1, we went from the real world to the math world. In step 2, we solved the problem in the math world. So in step 3 now, we want to go from the math world back to the real world. I want to take my mathematical analysis and use it to make conclusions about reality. So again, this is mathematical modeling is very subtle. It's definitely not easy. And in this particular case, in this particular class, the type of mathematical model we will look at will come in the form of a differential equation. There are many different types of mathematics, statistics, probability, So here we're specifically looking at a differential equation, which comes from calculus. So what's a differential equation? Well, first and foremost, it's an equation. So it has an equal symbol. it has a left-hand side, and it has a right-hand side. In this case, the unknown that we're looking for is actually a function. And this is an equation that involves, one or more derivatives of the unknown function that we're trying to find. So here, for example, if you look at this differential equation right here, I have y double prime equals negative y. Or we could also bring the negative y over and write it as y double prime plus y equal to 0. What you should notice, first of all, the unknown that we're looking for is the letter y. Here, the variable y is not known, and that's what we're trying to find. And in fact, it's not a variable. I say it's y is actually a function, because here we're taking two derivatives of this thing called y. So it must be a function. That's the only mathematical object we've defined derivatives for. If y were a constant, y double prime would just be 0, and this equation would just say 0 equals negative y, or y just equals 0. So if y is a constant, this is a boring equation, but here y is not a constant, it's in fact a function. And so here, I'm looking for a function, y of t. So typically with these mathematical modeling problems, the independent variable is time. So here I'm assuming y is a function of time. Can I change that to x? Absolutely. There's no, you can use whatever independent variable you want. So we're looking for a function y of t that satisfies the differential equation. So I use this phrase, satisfies the differential equation. What does that mean? It means I'm looking for a function y such that when I differentiate it twice, when I do y double prime, the answer I get back will be the original function I started with, but with a minus sign in front of it. Okay, that's what we're looking for here to solve this particular differential equation, y double prime equal to y. So here, since this is not a differential equations class, I'm not going to actually tell you how to solve that. But here, we can guess a solution. For example, if we guess sine of t, I'll show you that that turns out to be a solution. So what I'm going to now do is differentiate sine of t twice and show you we get back the original function, but with a minus in front of it. So here's y of t equal to sine of t. I take a first derivative, so y prime equals cosine t. And then I take a second derivative, so y double prime equals negative sine t. And now if we go back and look, well, sine t just equals y. So when we say y double prime equals negative sine t, what we're really saying is y double prime equals the negative of what we started with. Y double prime equals negative y. So here, the function sine of t will be a solution to this differential equation. And notice the solution here is not a fixed number, it's a function, sine of t. And in this case, because of the theory, which you'll learn when you take the differential equations class, because this is a second derivative here, y double prime, what we're expecting is two answers. And so I say, can you guess any others? And so cosine works. I'll let you check that cosine works, that if you take cosine, differentiate it twice, you'll get back the negative of what you started with. So now, in this particular section, we're only going to focus on one differential equation. We're only going to look at y prime equals ky. I also rewrote it in Leibniz notation, dy dt, that's the same as y prime, equals ky. This is the only equation or model. So here, when we say mathematical model, we're referring to a differential equation. So this is the only model we're going to look at in this section. Like I said, you'll take a whole class on differential equations just devoted to solving different differential equations. But we're just going to focus on this y prime equal to ky. So here, k is some constant. And as I said, y will be a function of t. I think it's really important not just to read it as an equation, but to really interpret it as a sentence. So here, dy dt the rate of change of y is proportional to the value of y. That's how that equation would be translated into an English sentence. At any time we have any phenomenon where the rate of change of that phenomenon is proportional to the value, then we can model it with this equation here, y prime equal to ky. And then once we solve that, we'll be able to describe whatever y is. So just a little bit of history. This equation is known as the exponential growth and decay model. It's also known as the Malthus model, which is named after Thomas Malthus, who suggested this model as a model for population. So they suggested that if we have infinite resources, then the population will satisfy this equation here, where y would be the value of the population. And remember, we looked at an equation very similar to this, and I said this is a feedback loop. So just let me emphasize the feedback loop component of this. So let's think about how this equation works. Suppose the left-hand side, k times y, is positive. Then the derivative will be positive, so this function will be increasing. If the function's increasing, then ky will get even bigger, and the derivative will be even steeper. And so you see this feedback loop where this function blows up to infinity, and here we expect the solution to be an exponential function. And if the left-hand side, if the right-hand side turns out to be negative, then you still have a similar loop. So if this turns out to be negative, then y prime is less than 0, so the function is decreasing. The function is decreasing, the right-hand side becomes even more negative. And so your derivative, decreases even more. I mean, your function, your derivative is even steeper in the decreasing direction. And so whether the left-hand side, the right-hand side is positive or negative, this gets locked into that feedback loop, and the shape looks like either an exponential function that's increasing or an exponential function that's decreasing. So here, as I said, population is a very common application of this model. It's not an ideal model, but it's a starting point. That's for growth. For decay, we model what's called radioactive decay using this exponential model. And this is because the amount of a radioactive material decays in proportion to how much there is. The more there is, the faster it'll decay. But Newton's law of cooling here, heat will pass from a warm body to a cold body depending on the temperature difference. So here for the heat example, think about a situation where you have two bowls of water. One bowl of water is very cold and one bowl of water is very hot. And we then drop an ice cube into each of those bowls of water. In one case, the ice cube will melt very quickly. And that's because the heat transfer is proportional to the temperature difference. And there are many other, applications, chemical reactions, laws of motion, viral epidemics. I don't know why I thought of that last one. So as I said, each of these phenomenon above, involves a rate of change. And when we try to describe the relationship, it takes on the form y prime equal to ky. And so this becomes our mathematical model for each of these phenomena: population, radioactive decay, Newton's law of cooling. So of course, that leads us to the next step of mathematical modeling. So this is our first step, is we've taken this physical situation and we're describing it with a mathematical equation. So now we should solve the equation. So you don't need to know how to solve this equation. What you do need to know is the result of this theorem. So you need to know that the solution to the differential equation dy dt equal to ky, where the initial condition is y of 0 equals y sub 0, you need to know that the solution to that is this function right here, y of t equal to y sub 0 times e to the kt. So you don't need to know how to solve it, you do need to know what the solution is. And yeah, I'm going to just go ahead and tell you to memorize it. Of course, let me prove it very quickly for you. Okay, so this uses a technique known as separation of variables that you learn in Calc 2, that you will learn in differential equations. I'm just really reluctant to throw a formula at you and ask you to memorize it. Okay, so let me do some math to justify it, and then I'll make you memorize it. Somehow that's better for me. I don't know if it's better for you. So separation of variables, the first step is I'm going to put all the y variables on one side. So I'm going to move this y over here, so it'll be dy over y, and move all the t variables to the other side. So when I separate the variables, you get dy over y equals k times dt. And be careful, dy dt isn't really a fraction, so we really can't separate these things. So what's actually happening in the background is like a u substitution. Okay, so I won't explain it. It'll come up later when you take Calc 2 and differential equations. But for now, accept that we can separate the variables this way. And so once I've got all the y variables on one side and all the t variables on the other side, we just integrate both sides. And here on the left-hand side, we're integrating, 1 over y dy. So the antiderivative of 1 over y dy is going to be natural log of absolute value. And on the right-hand side here, k is just a constant. So you can either pull it out, or you can just take the antiderivative of k dt, it will be kt, and then don't forget the constant of integration. So here, the antiderivative of k dt will be kt plus c. So I get natural log of absolute value of y equals kt plus c. So remember, I'm trying to solve for y, which is trapped inside the natural log. So now let me e both sides. I'm going to raise both sides to e, right? Exponentiate both sides. E to the ln, the e and the ln cancel, just gives me back the absolute value. So here I e both sides. And as I said, e to the ln just gives me the absolute value. So here they cancel. And here e to the kt plus c, using properties of the log, this is the same as, not properties of the log, properties of exponents. So x to the m plus n equals x to the m times x to the n. So here, e to the kt plus c equals e to the kt times e to the c. And I wrote the e to the c in the front here. Last step, I want to get rid of these absolute value bars. So I drop the absolute value bars and I write y equals plus or minus e to the c times e to the kt. So here, if this is a negative, when I take an absolute value, I'll get back e to the c times e to the kt. Or if this is a plus, when I take an absolute value, I'll still get back e to the c times e to the kt. So here I conclude y is plus or minus e to the c times e to the kt. And here, keep in mind, t is the only variable. T is time. It's the only variable. K is a constant that comes from the differential equation. And c is a constant that we got from integration. It's the constant of integration, okay? So here, since c is a constant, certainly e to the c is a constant. Plus or minus e raised to the constant will also be a constant. So let's just call that, once again, let's just call plus minus e to the c, since it's a constant, let's just call it c. We kind of play this bad notation game with the constants, So yeah, so now my solution looks like y equals a constant times e to the kt. Let me remind you, t is the variable. And here now I want to just apply the other piece of information that they gave us, which is what we call the initial condition. So at t equal to 0, we know y of 0 equals some constant y sub 0. So here, don't let the notation mess with you. Y sub 0 is just meant to be some fixed number. And it's the value of the function y at the time t equal to 0. So if we apply that condition here, we see that c equals y sub 0, because here when I replace t with 0, e to the 0 is just 1. So I get y sub 0 is equal to y of 0, but y of 0 is just c times 1, or c. So c equals y sub 0, and so when we put it all together, we get our answer to the differential equation is y sub 0 e to the kt. As I mentioned, you do not need to know the proof. You do not need to know this math that we just did. You do need to know the result. So you need to know the solution of this differential equation is this function over here. And, you know, as I said, I'm just going to ask you to memorize it. I will not talk about the uniqueness. So let me mention what the heck that means. So here we've shown that y sub 0 e to the kt is a solution. There still may be other functions that are also solutions. But the theorem actually says, no, in this case, the only solution is y sub 0 e to the kt. And so that's what I mean by uniqueness of the solution. That in this case, not only is y sub 0 e to the kt a solution, but it's the only function that'll satisfy this differential equation. Okay, so this is one of these subtleties of differential equations that you'll learn when you're talking about differential equations, okay? So here this theorem gives us the existence and uniqueness of a solution to this exponential growth and model differential equation. So yeah, I won't talk about the uniqueness, but the theorem tells us there's only one solution, and you know, it's this function right here. So let's now do some problems. So let me show you, the problems are a lot more straightforward than you think. There's very little actual calculus involved. So here, suppose y of t is the population of some organism at time t. So in general, it's been observed that populations grow at a rate proportional to the current value of the population. If I wanted to say that in math, we would say the rate of change of the population is proportional to the value of the population. That is y prime equal to ky. And if I know the initial population, so suppose the initial population is y sub 0, then I can immediately use the previous theorem and write down the solution, the function that tells me the population at any time t. I don't redo all of that math. I just say, from the theorem, we know the answer to this exponential growth and decay model is y of t equals y sub 0 e to the kt. So in this case, k will be a positive number and is called the relative growth rate or the intrinsic growth rate. So here's an example. The population of a bacteria grows at a rate proportional to its own population. After 3 hours, the population is 1,000 bacteria, and after 5 hours, the population is 4,000 bacteria. So the first question is, what is the relative growth rate of this population? And the second question is, how many bacteria were present initially? So basically what's happening here is this first sentence, the population of a bacteria grows at a rate proportional to its own population. That's telling us that if y represents the population, then we know y prime equals ky. That's literally what that sentence is saying. The population grows at a rate proportional to its own population. We're literally saying y prime equal to ky. And then we don't solve this. We immediately just say we know the solution is y of t equals y sub 0 e to the kt. This is the most important part I can tell you. It's almost too easy. This is all the calculus there is in this entire problem. The rest of this problem is just algebra. For you, the only part is to realize that here we can model the population using the exponential growth and decay model. And therefore, this must be the formula for the population. So now, what's the work that needs to be done? Well, y sub 0 is unknown, and k is unknown. And we're basically doing algebra. So you remember, if I have two unknowns, I need two equations. And luckily, quote unquote, luckily, they gave us two pieces of information. After 3 hours, the population is 1,000 bacteria. And after 5 hours, the population is 4,000 bacteria. So here now, the left-hand side y of 3, I can plug in a 3 for the variable t in my solution, y sub 0 e to the kt. And for y of 5, I can replace the t with 5 and set that equal to 4,000. So here, this equation y of 3 equal to 1,000 translates to y sub 0 e to the 3k equals 1,000, where I've replaced the t with 3. And this equation y of 5 equal to 4,000 translates to y sub 0 e to the 5k equals 4,000. So now, two unknowns, two equations, we're just doing algebra. For part A, we're specifically looking for k. So I'm going to set both of the equations equal to y sub 0. And since they're both equal to y sub 0, I can set them equal to each other. And now I'm going to cross multiply. This e to the 5k, I'm going to put it up here in the numerator position. And this 1,000, I'm going to put it down here in the denominator position. I cross multiply. And now e to the 5k divided by e to the 3k, that's e to the 5k minus 3k, that'll become e to the 2k. And of course, 4,000 divided by 1,000 is 4. And now finally, to solve for k, which is up in the exponent position, I'm going to take a natural log of e to the 2k equals natural log of 4. Natural log of e to the 2k, this is just going to be 2k because the ln and the e cancel. So I'm going to get 2k equals natural log of 4. And I'm trying to solve for k, so I divide both sides by 2. So I get k equals natural log of 4 over 2. And one last part, just to show you some manipulations that the book might do, I'm going to now take this 1/2 that's in the front, and I'm going to put it up here in the exponent position. That's a property of the log. And so here, I'm going to have 4 raised to the 1/2, which I can just write here. I wrote as square root, positive square root of 4 here. And so the k value, the relative growth rate is ln of 2. And ln of 2 is a positive number. How do I know ln of 2 is a positive number? Think of the graph of the natural log function. It crosses the axis at 1. So here I'm at ln of 2. And so you can see from the graph, ln of 2 will be a positive number. So once we've solved for k, now for part B, it says how many bacteria were present initially. So we're looking for y sub 0. And here we have two equations we can use to solve for y sub 0. I'll just go ahead and use the top equation. So the top equation here tells us that y sub 0 equals 1,000 over e to the 3k, where k we solved to be natural log of 2. So I replace the k with natural log of 2. Now watch, this 3 that's in the front, I bring it up to the exponential position. And here I have e to the ln of 2 cubed. The e and the ln cancel. I just get back a 2 cubed. Now I have 1,000 over 2 cubed, which is 1,000 over 8, which we can calculate to be 125 bacteria. I just want to make you aware of all these little mathematical manipulations that the book might do. And they will do that. They'll rewrite the answer, and it's sometimes confusing because they don't explain it, but they're using these properties of the log. So that's why I wanted to show you all these sort of little, it's not difficult, but these little calculations that you should be aware of, that we can do these types of things. Take advantage of the fact that E and ln are inverses, so we can simplify it. So the other big application is the radioactive decay. So this time, Y of T represents the mass of some radioactive isotope that we have. And the theory is that the radioactive isotope decays at a rate proportional to its amount. The more there is, the faster it'll decay. The less there is, the slower it'll decay. It's kind of like when snow melts. You know, at the beginning, it melts very fast, but then it kind of starts to slow down. So here, we can model the mass of the radioactive isotope, where Y represents the mass, is Y prime equal to KY. And then we know from the theorem, the solution is Y of t equals Y sub 0 e to the KT. So we have a formula that tells us how much radioactive substance we have at any time t. You know, and that's all the math we have to do. I'm not resolving the equation. In this, K will be negative. It'll turn out K will be negative, and this will be known as the relative decay rate. Here, the mass is decreasing, unlike the previous example where the population is increasing, so K is, you know, positive. Here, the mass is decreasing, so K is negative. By the way, we define this thing called the half-life. So the half-life of a radioactive substance, I don't think the textbook uses this notation, but most scientific books use the notation T sub 1/2 for the half-life. So it's basically just the amount of time that we need for the substance to decay to half its original amount. So if I originally had 100 kilograms of some radioactive isotope, then the amount of time it takes to go from 100 kilograms to 50 kilograms would be the half-life. Okay, and we can actually solve for it. It's really mathematically not difficult. Here, I'm setting the amount of radioactive material I have, which is Y of t, equal to 1/2 the original. And then Y of t, I replace with this function here, Y sub 0 e to the KT. And then we cancel the Y sub zeros on each side. This Y sub 0 cancels with this Y sub 0. So I have e to the KT equals 1/2. So you then take the ln of both sides. So you get KT equals ln of 1/2. So then solve for t, we get t equals ln of 1/2 divided by k. Okay, so I'll let you think about that, but the math is, you know, just algebra. So here's an example. The radioactive isotope bismuth 210 has a half-life of 5 days. Don't let this number 210, you know, confuse you. That has nothing to do with the problem. It's just part of the name of bismuth. You know, COVID-19, bismuth 210, sorry, too soon. So yeah, it has a half-life of 5 days. So they say find the relative decay rate and find the mass after 30 days if initially there was 800 milligrams of the substance. So here we're modeling the mass of bismuth 210 with the exponential decay model. And so if Y of t is the amount of bismuth 210, then we know Y of t will equal this function, Y sub 0 e to the KT. There's no other backstory that's necessary. Here, we're assuming the exponential decay model, and the solution to the exponential decay model is Y sub 0 e to the KT. You know, this is how differential equations goes. It's a slightly different style of math where it doesn't even feel like, wait, that's all you have to do? Yeah. So now we just have to find Y sub 0 and K, essentially. Actually, we know Y sub 0. So let's see. We have to find the mass after 30 days. So we have to find Y of 30. And for part 1, we have to find K. So let's use the information that's given. They tell us 5 is the half-life, 5 days. So what does that mean? Y of 5 equals 1/2 of the original amount. And here, even though I do know the original amount was 800 milligrams, I don't need it, because if you look, what happens in the math is we actually end up canceling the Y sub 0. So whether I knew it or not, it wouldn't matter here for this calculation. So I'm trying to solve for K, take the natural log of both sides. The natural log and the exponential function are inverses, so bring, you know, you just get back 5K. And here, the 1/2, I wrote that as 2 to the -1. And then because it's in a natural log, I brought the -1 down in front. So that's where this minus sign's coming from here. So I write 5K equals negative ln of 2. So finally solve for K. I get K is negative ln of 2 over 5. I know ln of 2 is positive. I know 5 is positive. So I know the quotient here is going to be negative because it's negative ln of 2 over 5. as I expected, because this is the decay rate. So finally, they say, find the mass after 30 days. So I'm looking for y of 30. So in this formula, I'm replacing the t with 30. And so right here, you can see there's the 30 for the t. I'm replacing the k with this mess, minus ln of 2 over 5. So here's the k, minus ln of 2 over 5. And then we're told initially there's 800 milligrams. So this y sub 0 in the front, I'm replacing with 800. So there's our y of 30, 800 times e raised to the negative ln of 2 divided by 5 times 30. And so now I just do a little math. Here, there's a 30 here, which I divide by 5. And so this 30 divided by 5 gives me 6, which I wrote right here. There's, of course, the minus sign in front. Now this negative 6, I'm going to put it up here in the exponential position. So this becomes e to the ln of 2 to the negative 6. And the e and the ln cancel, and we just get back a 2 to the negative 6. Finally, I'm able to simplify 800 divided by 2 to the negative 6, or 800 over 2 to the 6, because 800 is also even. I'm able to simplify it down to 25 over 2, and I'll let you verify that that's correct. So this would be an example of, where we have exponential decay. And as I said, there's not a lot of math in terms of calculus. Once we just identify that we have the exponential growth or decay model, we can just write down the answer. And then typically it's just a lot of algebra. So here's Newton's law of cooling. So this is one final application. You don't need to know Newton's law of cooling. You just need to know the solution to the exponential growth and decay models. So here, careful of the notation, capital T of little t is the temperature. So capital T is the temperature, little t is time. Okay. And here, capital T of S is the surrounding temperature. So T for temperature, little s for surrounding. So Newton's law of cooling. So this is the part where we're kind of taking a physical phenomenon and converting it into some kind of mathematical sort of statement. And so Newton's law of cooling says the change in the temperature of an object is proportional. It's related to the temperature difference between the object and the surrounding temperature. And again, it's important that you do the thought experiment where you think of, I have 2 bowls of water. One is very cold, one is very hot. I drop an ice cube into each of those bowls of water. One ice cube will melt a lot faster than the other. And it's exactly because of this principle. It's exactly because of the larger temperature difference, you have a greater temperature change. So now let's put this in a mathematical equation. So here's exactly this sentence converted into math. So if I take this sentence, convert it into math, here's what we get. And let's read it. The change in the temperature is proportional to the difference between there's minus sign, between the temperature of the object and the temperature of the surrounding. So that sentence, if you convert it to math, looks exactly like this equation. The change in the temperature is proportional to the difference between the object's temperature and the surrounding temperature. So now let's solve this. It's not difficult. It's actually just a little sneaky trick. Let this t of t minus t sub s, call this whole thing, just call it y, the function y of t. So be very careful. Remember that t sub s is a constant. The only function with the letter little t in it, the only function here is capital T of t, okay? So if we call capital T of t minus t sub s y, so I have that written down here. And now let's take a derivative of both sides. Because t sub s is a constant, the derivative will just be dy equals of the temperature, the derivative of the temperature. So here, you should, if y equals the function t minus the constant t sub s, then dy dt will just equal the derivative of the function t. And the derivative of the t sub s part is just 0. So what happens is I can replace dt dt with dy dt, and I can replace capital T minus t sub s with y. And so we get back our usual, exponential growth and decay model. Here, this y is the same as t minus t here. And on the other side, the dy dt, that's the same as dt dt. And so now I don't need to solve this, guys. I know by theorem 2, the solution is y equal to y sub 0 e to the kt. And now I'm going to replace y with what I originally substituted for. I'm going to replace y with capital T minus T sub s. So there you see it. Here's y replaced. And then for y sub 0, I can calculate y sub 0 is just y evaluated at 0. It's y with little t equal to 0. So here in this function, if we let little t equal to 0, we get y sub 0 is capital T of 0 minus t sub s. One final step, I move this constant over to the other side. It can't combine with anything. These terms in the parentheses are being multiplied by this exponential function, so it doesn't combine anything. It just hangs around out front right here. And so here, T of t, that's the temperature of the object at any time t. And here's a formula on the other side that'll tell us the temperature at any time t. And here I say I expect k to be negative. Why? Because after a very long time, like as t goes to infinity, I expect the temperature of the object and the room temperature to be the same. Like for example, the example with the 2 bowls of water, when t goes to infinity, regardless of which bowl of water, the hot or cold, if you wait long enough, they'll both just come down to the temperature of the room. So here's t goes to infinity. I'm expecting this term to go to 0. When this term goes to 0, then we will get, the temperature of the object after a long time is the same as the temperature of the surrounding. So that's why I say I'm expecting k to be negative, because I'm expecting this part to decay. So here, let's do a quick problem, and then I'll stop. It says soup is cooled from 90 degrees to 60 degrees after 10 minutes in a room whose temperature is 20 degrees. Find the temperature of the soup at any time t. So first of all, when they say soup is cooled from 90 degrees, 90 degrees is our initial temperature of the soup. So in T of 0, the initial temperature of the soup is 90 degrees. And then they say they're in a room whose temperature is 20 degrees. That's the surrounding temperature. So 20 degrees would be T sub s. T sub s would be our 20 degrees. The only piece of information we don't know is K. But luckily, they give us one more piece of information. They tell us after 10 minutes, the temperature is 60 degrees. So here, we should be able to do the algebra and find everything. So here's the temperature function. So I said the initial temperature of the object, which is the soup, is 90 degrees. The surrounding temperature is 20. And so I'm just plugging everything into this formula right here. (20 plus parentheses 90 minus 20 e to the kt). 90 minus 20 is 70. So I just simplified this part. 90 minus 20 is 70. And so now we have everything except K. So now let me use the fact that the temperature is 60 degrees after 10 minutes. So T10 equals 60. So I plug that in, set it equal to the function. And now we're just doing algebra. I want to isolate this term, the e to the 10k term. So I'm going to move the 20 to the other side. 60 minus 20 is 40. and 40 I'm going to divide by 70. So I have e to the 10k equals 40 over 70. And now take the natural log of both sides. Take the natural log of e to the 10k, and here 40 over 70 would be 4/7. Take the natural log of 4/7. So the natural log and e cancel. So on the left-hand side here, I have 10k equals ln of 4/7. Solve for k. And then I plug the k in, and there's my final answer. So these exponential growth and decay problems aren't difficult in that we know the answer already. With all of these problems, you know, the answer is always going to be some variation of y equals y sub 0 e to the k2. Okay, so there's 2 more slides left. I'm going to let you read those on your own. You know, they might be similar to some of the problems you'll see in the homework. So I'm going to stop right here, everybody.